You know, every single time a pilot pushes the throttle forward for takeoff, they have to make a choice, a really fundamental choice about how they're going to climb. It's not just about getting off the ground, it's about the whole geometry of the ascent. So let's dive into this critical decision between two key airspeeds, Vx and Vy.
So let's just ask the basic question, what's the priority right after takeoff? Is it to gain as much altitude as you can over a super short distance on the ground? Or is it all about getting up to your cruising altitude in the shortest amount of time possible? This choice right here is at the heart of everything we're about to explore.
And really, it all comes down to understanding these two speeds. Over here on the left, you've got Vx. That's all about the best angle of climb. Think of it as, how steep can I go? You're trying to get the most altitude over the shortest horizontal distance. But on the right, you've got Vy, which is the best rate of climb. That's all about gaining altitude in the shortest amount of time. So distance versus time, that's the game. All right, so angle versus rate. What do these terms actually mean when you're in the cockpit? Let's break down how they translate into actual flight. Okay, so Vx. This is your go-to speed when you've got an obstacle at the end of the runway, like a line of tall trees or a building. You absolutely have to create the steepest possible flight path to get up and over that thing safely. It's all about maxing out your climb angle relative to the ground. Here's a great way to think about it. If there's a huge wall right in front of you, you don't want a long, shallow ladder, right? No way. You need the steepest, most direct ladder possible to get up and over it, while taking up the least amount of ground space. That's exactly what Vx is. Okay, now let's switch gears to V. This speed is a whole different animal. It's not about clearing obstacles right in front of you. It's about pure performance against the clock. V gets you the maximum feet per minute on your vertical speed indicator. It gets you to a higher altitude faster than any other speed. And the analogy for VG? Well, it's like an escalator. Sure, it might cover more ground than that steep ladder we talked about, but it is absolutely the most efficient way to gain height over time. This is your express ride up to cruising altitude. So what's the actual physics making this happen? It really comes down to two different ideas, thrust and power. Vx happens at the point of maximum excess thrust. Just think of that as the biggest possible surplus of forward force from the engine, after you've overcome drag. That extra push is what you use to climb up. Vy, on the other hand, happens at maximum excess power. And since power is just thrust times your speed, it's really about how quickly you can do the work of climbing. So one is about raw force, the other is about the speed of getting the job done. Okay, so theory is great, but how does this all play out in the real world? This brings us to the practical stuff, obstacles, the very real risks involved, and the procedures pilots use to manage it all. So let's walk through a classic short-field takeoff. First, the pilot gets the plane configured, holds the brakes, and goes to full power. Then they rotate, pitching immediately for that steep Vx climb. They hold that nose-high attitude just long enough to know they're clear of the obstacle. And as soon as they are, they lower the nose, let the plane accelerate to the more efficient Vy speed, clean up the flaps, and continue their climb. It's a really precise sequence of events. But, and this is a huge but, here's where the story takes a sharp turn. One source put it incredibly bluntly. Vx is a single-purpose tool. And you know what? It's also the most dangerous climb speed. This is not a speed you hang out at unless you absolutely have to. So why is it so risky? Well, there are a few big reasons. First, climbing at Vx means you're flying slower, which puts you uncomfortably close to your stall speed. Not good. Second, if your engine quits, you just have less total energy to work with. You have to shove the nose down really aggressively to get to a safe gliding speed, and you lose a ton of precious altitude doing it. Plus, the reduced airflow can cause the engine to overheat. But the most critical part? If that engine fails, a pilot's delay of just 4 seconds can be the difference between recovering and entering a stall. It's that serious. The best way to get this is to think about an aircraft having two different batteries of energy. You have potential energy, that's your altitude, like a battery of height. And you have kinetic energy, that's your airspeed, a battery of motion. In an emergency, you can trade one for the other. At Vx, you're flying slow and low. Both of those batteries are pretty drained. But here's where it gets even more interesting. This whole relationship between the best angle and the best rate, well, it's not set in stone. As an aircraft climbs higher into thinner air, something pretty fascinating starts to happen. See, as you climb higher and higher, the air gets thinner, right? And that does something really weird to these speeds. The speed for your best angle, Vx, actually starts to increase.
At the same time, the speed for your best rate, Vy, begins to decrease. They actually start moving towards each other on the airspeed indicator.
They keep creeping closer and closer together until eventually they meet at a single point. And this point has a name. It's the aircraft's absolute ceiling. It's the maximum altitude where the plane just physically can't climb anymore.
For your classic Cessna 172, this all happens right around 16,000 feet. At that altitude, Vx and Vy have become the exact same speed, and your climb rate is, well, it's zero. The plane just can't go any higher. That's the roof.
So, let's just recap for a second. We've got this steep, optimal angle that's pretty risky, and we've got a faster optimal rate that actually changes as you climb. It all leads to the big final question. How on earth does a pilot choose the right climb speed?
So after all of this, what's the best speed? If you're looking for one simple answer, I've got bad news for you. There isn't one.
The reality is, it's not about one single best speed. It's a complex decision, a judgment call, that a pilot has to make before every single takeoff. It depends on everything from the airport's elevation, the terrain, the plane's weight, and even how familiar the pilot is with the area. It's a dynamic calculation every single time. And to make it even more complicated, it's not just a two-horse race between Vx and Vy. Pilots also use what's called a cruise climb, or VCC. This is actually faster than Vy. What you're doing is trading a little bit of your climb rate for more forward speed. You're cashing in some of that potential energy, height, for more kinetic energy, airspeed, which can be a much safer place to be.
And that's really the key takeaway here. Picking a climb speed isn't just about reading a number off a chart. It's a dynamic risk assessment. It's a trade-off between different energy states, and it's a critical choice about the geometry of survival, all made in the first few moments of every single flight. What seems like such a simple decision is actually one of the most complex judgments a pilot can make.